Hey everybody, gonna go ahead and do a little video version of something that we talked about in our little conference yesterday and kind of put it into YouTube so that way it's just there and easier to access. But it's on center of mass and velocity of center of mass. And this is something that we touched on earlier in the year, but the velocity of center of mass is kind of an important big deal for physics, at least for the AP Physics 1 exam. So the idea being that if you've got, let's say, a couple of particles, kind of draw one here, call that particle number 1, and another particle over here called 2. And if they exist on some sort of one-dimensional number line that's measured in meters, the positions of those are distinct. You have one at position 0, the other at position 4, and where they are, they're separated by space, but there's a point somewhere that we call the center of mass that exists between them that we can think of as a balancing point. You know, if these objects were on a light rigid rod, maybe some sort of like connecting rod like that, where would we put a pivot on that rod to balance the system out so that torque on each side of that pivot would be equal? It's one way to think of it. Another way is that if this was two objects that were somehow together, and if we zoomed out really far, we would have to say that it sort of looked like a single point, and where would that point be? Well, it wouldn't be at object 1 or object 2, it'd be someplace in the middle. So that's what the center of mass is. It's not necessarily the center of geometry, but it sometimes is. So here, we've got mass M1 and M2. Go write that up here. And if you had to guess with these two objects where the center of mass is, it's tempting to say that the center of mass would be located right there, smack dab in the middle. And that is a center, but it's the center of geometry. It's halfway between each point. We can find that by taking an equation saying, what if we call it CG, not for center of gravity, that's maybe not the best notation, but just by averaging the positions, the position of object 1 plus the position of object 2 divided by 2 positions, just finding the mean value there, then that would give us 2 meters because you have 0 and 4 halfway between them. It's 2. That makes sense. That's our center of geometry, but that's not what we're looking at here. Center of mass is a weighted center of geometry. It's saying that, yeah, if they were equal masses, the point that we would call the center mass would be halfway between them. But if one of them's bigger than the other, that's going to require us to shift the center of mass. And the question is, where do we shift it? Is it a little bit closer, much closer, or is it basically right on the object number 2 if that was the bigger object? So if I say that this is 1 kilogram and this is 4 kilograms, if I think of the center mass as being a balancing point for that teeter-totter action, it's kind of common sense to say that, well, the pivot for that teeter-totter, the fulcrum, would have to be closer to the heavier object. You just know that from being a kid sitting on a teeter-totter. Hopefully you had that experience as a kid. And you know that you have to put that pivot point further over because that heavier thing, if you put it as far out, it's going to torque the system down. So you need the light object further out and you need the heavier object closer into the pivot, and then it can be balanced. So in the case of the center of mass, we have to then weight this calculation for position. We can't just say that, sorry, had to pause, my phone was vibrating in my pocket like crazy. Spam emails, nothing important. So we can't just do the positions. We have to include the masses in there. And that's where the equation that we have below lines up. It doesn't just have the positions, it has positions times mass. And you can kind of think of this like weighted grading scales in a class. If your teacher has tests and quizzes are worth 60 or 70% of your grade, and a 10-point quiz is not going to impact your grade the same as a 10-point bookwork assignment that might only be in a category worth 15% of your grade. So those 10 points are not equal. So a meter is not equal depending upon positions, for positions in a system like this if the masses are different. They weight the system differently. So we end up taking the position times the mass for each object and then dividing it not by the total number of things, but the total number of kilograms of mass that we have. So in our example up above, the center mass would be 0 meters times 1 kilogram plus 4 meters times 4 kilograms, all divided by 1 kilogram plus 4 kilograms. And that would give us 16 over 5, or 3.2, which would be somewhere about here. That position that I put the big red dot in, that's what we would call the position of the center of mass. Now, let's go ahead and take a look at a simulation version of that. I've got here the PhET simulation called Collision Lab, and I have, let's go ahead and change the numbers of these to reflect what we were just talking about, move them kind of farther apart. I've got these two objects, and this allows me to play a collision simulation and have them hit. I have it very slow right now, but there's an option for center of mass that that puts a red X, it's yellow, puts a yellow X where the center of mass is for this system. And as you can see, it's much closer to that object number 2 that has a greater mass. But the nice thing about this is that it allows me to change the simulation on the fly. And if I decrease the mass of object 2, that center mass starts getting really close and then exactly halfway between the two objects. So this equation gives us the position of center mass. Let's go ahead and take a look at the velocity of the center mass. And the nice thing about that equation is, technically speaking, we just take the first derivative of the position of center mass, and that formula gives us the equation down below with the velocities. But we can also just think of it as swapping all the positions for velocities. I guess I should say swap v for x. So we just take all the x values and we replace it with v values. And this is an important change because as object 1 gets closer to object 2, if that's the only one that's moving, that means that its position has to get updated in that position equation, which means the center mass position needs to be updated as well. And as object 1 moves closer to object 2, the center mass will also move closer to object 2 as well. And let's take a look at it right here. Got that little yellow X. If I click play, it's always smack dab in the middle between the two objects, all the way to the point where they're about to hit as well. That center mass is always right in between them. So this equation, go ahead and actually get the reset button there. The equation we've got is pretty straightforward, but here's the trick. Yeah, we can calculate with that, but the big catch here is that if two objects collide, what happens to the center mass velocity? If you have that picture that is had with object 1 getting closer to object 2 and they hit and they bounce off of each other, it's an elastic collision, what's going to happen to the center of mass? Does it keep going the same way? Does it speed up? Does it slow down? Does it reverse direction? In a complicated collision where both things are moving quickly, what happens? Well, the big idea here is that the center mass velocity does not change. It stays constant. So let's take a look at why. On this equation, on the top, instead of x times m, we have v times m. Well, momentum is the same thing. It's m times v, v times m. You swap them around. So that's the momentum of object 1. Then we have v2 times m2. That's the momentum of object 2. And I have the sum of the momenta of the objects all divided by their total mass. Well, this right here is just total momentum. And does total momentum change when two things collide? No, it doesn't. Total momentum is constant. That's how conservation of momentum works. So this equation is saying that the center mass velocity, that yellow X on my diagram, undergoing a collision where it's an isolated system, just those two things interacting, the center mass velocity will be constant. It'll be constant because it's total momentum divided by total mass. And the total momentum does not change. Now, reading is not believing. Let's go ahead and take a look at the simulation again. Here I've got the yellow dots. Go ahead and click play. follow that yellow X as it goes along. I keep my mouse underneath it. They collide, and it's still going the same velocity. They end up bouncing off of each other, but they're the same mass. Maybe that's not as convincing. So how about we change it so that this one has mass 4, like we had in our simulation. The center mass is really close there. I click on it, see the center mass moving closer and closer to the center of 2. They collide. The center mass keeps moving, even though they're both moving now. And we can change this simulation wildly. We can have them both moving towards each other. That yellow X is not going to change how it's moving after the collision. Still going. Even if they stick together, same thing happens. I'll turn elasticity down to 0. Keeps on going with them. So all collisions in an isolated system with 2 or even more objects, the center mass velocity does not change because it's calculated as the total momentum of the system divided by the total mass.